Hello, everyone. I'm Sunghyun Choi from Samsung Research, where I'm currently heading the Advanced Communications Research and Standardization, including 6G, beyond 5G, and IoT connectivity. I'm very happy to be part of IEEE VTC 2021 Fall Edition as a keynote speaker. In this talk, I would like to share our view on 6G towards the next hyper-connected experience for all. Before starting the technical talk, let me briefly introduce Samsung Research, where we secure state-of-the-art technology and maximize the synergy of technological convergence. We are constantly seeking and exploring new areas of AI, data intelligence, robotics, visual technology, and security to prepare for the future business of Samsung Electronics. Apparently, next-gen communications is one of the core areas of Samsung Research. While Samsung Research has the headquarters in Seoul, Korea, it has global R&D networks including 14 R&D centers in the US, Europe, Southwest, Southeast Asia, China, and Japan, and 7 AI centers in the US, Canada, the UK, and Russia. Now let's talk about the cellular mobile communications. As we all know, it has evolved from the first generation, which was introduced in around 1984 with analog voice communication, and now up to 5G, which we are enjoying today. Thanks to 4G, we could start enjoying true wireless internet. And that was a really big thing along with the introduction of smartphones. And now 5G is enabling unified and vertical services. I'm very proud to share that Samsung was the enabler of the world's first 5G commercialization back in 2019. We introduced the world's first 5G modem back in August 2018. And then in April 2019, the world first 5G commercial service started with Samsung's smartphones and network equipment. As of the first quarter of this year, 162 operators in 68 countries are providing 5G services. And over 389 million subscribers are enjoying 5G services in the world. In fact, Asian Pacific region is leading the commercialization with over 300 million subscribers, while America is catching up with over 50 million. As you might know, 5G KPIs were defined by ITUR in 2015, and then 5G technology was developed by 3GPP with 3 pillars of services in mind, namely ultra-fast enhanced mobile broadband, instantaneous true ultra-reliable and low latency communication, and finally, massive machine type communications. And to support these services, 5G was defined to support up to 20 gigabps peak data rate, 1 millisecond air link latency, and also support 1 million devices per square meter, and so on. While the 5G deployment is still ongoing, 5G standard itself has been evolving. In fact, global scale commercialization was enabled with 3GPP Release 15, and then Release 16 and 17 have focused on completing what were not fully addressed in Release 15. In fact, beginning Release 18, a new brand name called 5G Advanced will be used, and it will try to address the new market needs as well as the key issues identified during the initial deployment of 5G. One key issue which 5G Advanced will try to address is the coverage issue. Since 5G is using time division duplexing or TDD in high frequency bands, it results in the transmission coverage reduction, especially for uplink transmission. 5G Advanced will try to tackle this uplink coverage problem. Also, embracing new technologies into 5G Advanced is another issue. In particular, AI ML technology can be embraced so that it can enhance the performance and reduce operational complexity. Supporting new technologies and new device types, such as drones and XR devices, should be another homework. Finally, 5G Advanced will be defined to operate at diverse frequency bands up to 71 gigahertz for licensed, unlicensed, and shared usage. We are enjoying 5G today, and 5G itself is evolving towards 5G Advanced, as I discussed just ago. At the same time, industry and academia started talking about the next generation, so-called 6G. If you take a look at the right bottom figure, we see that a new generation has been introduced roughly every 10 years. Given that 5G is called officially IMT 2020, we can imagine that 6G will be defined to be IMT 2030 so that it can be standardized and commercialized around 2030. Now let's move on to 6G, which is going to open up a whole new world of opportunities in the following decade. Overviewing the mega trends towards 6G will be useful for us to predict what 6G should look like. First of all, 500 billion machines are expected to be connected by 2030, and it represents almost 60 times the world population then, meaning that machines along with human beings will be the main users of 6G. Especially, as shown at the right bottom table, the capability of machines can be far beyond that of human beings. Accordingly, 6G should be developed to meet the requirements of such highly capable machines. AI ML technology is being utilized for performance enhancement and automation in various areas, and mobile communication is not an exception. AI ML can be utilized for network planning, performance prediction, and optimization of mobile communication, so that CapEx and OpEx can be reduced. This trend is expected to continue, especially given that the mobile communication network is too much complicated to be monitored and configured manually. And the AI ML technology itself will continue to fast develop. While the network equipment has been heavily hardware-centric traditionally, more and more software-based solutions are being introduced thanks to the performance improvement of CPUs and GPUs. Along with that, use of open sources and open interfaces among network entities is becoming more popular too. This trend will allow us to build network in a more cost-effective and flexible manner. Accordingly, it should be an opportunity while there could be risks and challenges at the same time. Finally, communications technology has been contributing to address social issues such as greenhouse gas reduction and education inequality. And it will continue with 6G. In fact, 6G should be developed to be a more eco-friendly green technology. Given these megatrends, we expect that 6G will enable such exciting new services as truly immersive extended reality, or XR, high-fidelity mobile hologram, and digital replica, so that it will provide the next hyper-connected experience for all. While some of earlier forms of these services are available even today, they are not up to the customer satisfaction due to the lack of supporting technologies, including devices and communications technology. Today's 5G is not likely to be able to support full-fledged form of these services. To enable them, 6G should provide a lot better performance than 5G, including peak data rate of 1 terabps, which is 50 times that of 5G, and air link latency of 100 microseconds, which is 1/10 of that of 5G. We led 5G advanced technology back in 2009, and now we are at it again with 6G. We are currently looking at various candidate technologies to realize 6G. Those include terahertz bands, novel antenna technology, advanced duplex technology, comprehensive AI, and new network topology. I will talk about some of them in the following. 4G was defined to operate at up to 6 gigahertz, while 5G is being defined to operate at up to 110 gigahertz. To support the anticipated ultra-high data rate, we need to explore even higher frequency bands, say above 110 gigahertz. These high frequency bands, so-called terahertz or sub-terahertz, will allow us to utilize wide bandwidth needed for potential 6G services, as well as high precision sensing capability. However, there are many inherent challenges, including severe path loss and atmospheric absorption, poor RFIC performance, especially low power amp efficiency, and so on. Of course, 6G will also need to use lower frequency bands, which have been used for 4G and 5G in a more efficient way as well. In fact, we have already demonstrated the feasibility of terahertz communication. As shown in the slide, the demo included a transmitter and a receiver. composed of a 128 element antenna array and 140 gigahertz RFIC, which enable sharp beamforming along with the baseband modems. As shown in the video, the communication link achieves over 6 gigabps data rate. For the signal reception, the receiver uses a sharp beam formed by utilizing antenna array and RFIC. We observe that the data rate remains about the same, even if we rotate the receiver, meaning that the receiver's beam is formed towards the transmitter adaptively, irrespective of the receiver's orientation. We believe that this demo made a notable progress in terahertz communication development, given that this kind of adaptive beamforming technology is crucially important to support high-frequency communication link in mobile environment. We'll continue to develop terahertz communications technology so that it can be used as a key component of 6G. With 5G, massive antenna technology was introduced, and we expect that even more massive antennas will be used for 6G terahertz to compensate the path loss, low power amp efficiency, and so on. We believe that metamaterial technology can be used in conjunction with massive antenna technology to enhance beamforming and signal propagation properties, potentially at a reduced cost. Metasurface lens and reconfigurable intelligent surface, or RIS, are such good examples because they can adjust the beam direction of either penetrating or reflecting signal to enhance the communication quality. Frequency division duplexing, or FDD, has been widely used for up to 4G, and time division duplexing, or TDD, is mainly used for 5G today. We are introducing a new duplex scheme called XDD, meaning cross-division duplexing, as a means to extend the uplink communication coverage in TDD band as part of emerging 5G advanced standardization. XDD is developed to support simultaneous uplink and downlink transmissions using neighboring subbands with very narrow guardband within the TDD bands. 6G is expected to utilize all different types of duplexing schemes, including FDD, TDD, and XDD, in an adaptive manner depending on the environments. This will also include full duplex, which allows simultaneous transmission and reception over the same spectrum. In fact, we recently demonstrated full duplex technology over millimeter wave bands around 28 gigahertz. As shown in the slide, a base station and a mobile terminal were placed with 100-meter distance in an outdoor environment, where simultaneous transmission and reception occur with 100 megahertz bandwidth. This video shows the comparison between full duplex and TDD of 5G in terms of the total data rate, including both uplink and downlink. With full duplex, over 700 megabps data rate is achieved, which is almost the double of the total data rate achieved with TDD. Due to the protocol overhead and residual self-interference, full duplex can achieve slightly less than the double. We believe that full duplex will be a key component of 6G advanced duplex scheme, which allow us to utilize precious wireless spectrum more efficiently. As I mentioned earlier, AI/ML technology is being utilized for network planning, prediction, and performance optimization today. However, given that the technology up to 5G has been developed without AI/ML in mind, the improvement opportunity might be limited. We believe that AI/ML will be another important key component of 6G, and hence 6G will be developed with AI/ML embedded natively so that AI/ML technology can be used to optimize the end-to-end performance from user device to application server in a comprehensive manner. That is, while AI/ML can be used to enhance the performance of either user device, base station, core network, or application server locally, the performance optimization can be conducted by applying AI/ML to multiple entities jointly, and even to end-to-end path so that the entire network and service performance can be optimized. Last but not least, we expect the network topology will continue to evolve to provide high-performance 6G connectivity anywhere, anytime in a cost-effective manner. 6G should be available across the globe from the South Pole to the North Pole without service disruption. To meet the goal, 6G network should involve both traditional wireline and wireless backhauls, and even non-terrestrial networks such as satellite and urban air mobility. It should also make network entities automatically configurable and optimized while supporting user mobility and connectivity in a seamless manner. Last year, we released our 6G white paper, including our vision, various requirements such as performance, architectural, and trustworthiness requirements, and candidate technologies, which I briefly introduced today. Given that 6G is aiming for commercialization around 2030, its development will be a long, sweaty journey. We'll carry out our vision to bring the next hyper-connected experience to every corner of our lives in the following decade. Thank you very much for your attention and interest.